So now dear student, we will discuss about the collision, last point of the chapter, that is the collision. So when the two bodies of the different mass are colliding with each other, how the law of conservation of the linear momentum and law of conservation of the energy is satisfied. So for that, consider two bodies having a mass m1 and m2 is moving with the some initial velocity. So here consider the object m1 is moving with the initial velocity v1I with the, so here consider a object of a mass m1 moving with the some initial velocity v1I colliding with the another object of a mass m2 which is stationary. So we can say that the velocity of the second initial velocity of the second object v2I is a 0. Now after collision, the colliding objects are moving with the different velocity. So here the object m1 after collision, the object m1 is moving with the velocity v1f and object v2 m2 is moving with the velocity v2f. So during this collision, if we consider the linear momentum before the collision and linear momentum after the collision. So during the collision, linear momentum must be satisfied. So we can consider the linear momentum before the collision. Before the collision, the object having a mass m1 and m2, the initial velocity of the first object is v1I and initial velocity of the second object is 0. Why? Because the second object is at a race. So linear momentum before the collision, pi, initial linear momentum is linear momentum of the first object m1 mass and the velocity of the object v1I. So m1 into v1I plus linear momentum of the second object m2 into v2I, but here v2I is a 0, so we take the linear momentum, initial linear momentum of the second object is a 0. So linear momentum before, total linear momentum before the collision is a pi is equal to m1 into v1I. Understand? Now after collision, the m1 object is moving with the v1f velocity and m2 object is moving with the v2f final velocity. So after collision, the final linear momentum pf is equal to m2 into v2f plus m1 into v1f. So here the linear momentum must be conserved, right? Similarly, we can say that the kinetic energy is also, we can calculate the kinetic energy. So here the object m1 is moving with the velocity v1I. So the kinetic energy before the collision ki is equal to 1 half m1 v1I square plus 1 half m2 v2I square. I for the initial, right? So kinetic energy before the collision and linear momentum before the collision. So what is the linear momentum before the collision? Linear momentum before the collision pi, initial linear momentum m1 into v1I, because the mass of the first object m1, velocity of the first object v1I, plus mass of the second object m2 and the velocity of the second object v2I. But here if we consider the second object stationary, v2I is a 0. So we take the linear momentum pi is equal to m1 into v1I. So what amount the kinetic energy associated with the system of two objects? So kinetic energy of the first object, kinetic energy of the second object. So kinetic energy before the collision ki is equal to 1 half m1 v1I square plus 1 half m2 v2I square. Here also if the second object is stationary, we can take the v2I is equal to 0, right? Now after collision, what amount of the linear momentum of the colliding object? So after collision, the final linear momentum Pf is equal to m2 into v2f, m1 into v1f, right? And kinetic energy is equal to, final kinetic energy kf is equal to 1 half m1 v1f square plus 1 half m2 v2f square. Now here the during the collision, right, the linear momentum remains constant. and the kinetic energy remains constant, because according to the law of conservation of the linear momentum, initial linear momentum and the final linear momentum are same. So change in the linear momentum is 0, change in the kinetic energy is 0. So during the collision, if the linear momentum and the kinetic momentum remain same, right? So change in the linear momentum and the change in the kinetic energy is 0. The collision is said to be a elastic collision, or we can say that the completely elastic collision. So what do we mean by the elastic collision? During the collision, if the total linear momentum and the kinetic energy remains same, or we can say that the change in the linear momentum and the change in the kinetic energy is 0, the collision is said to be a elastic collision or completely elastic collision, right? So in the completely elastic collision, the initial linear momentum is equal to final linear momentum, or we can say that the initial kinetic energy is equal to final kinetic energy. So if the linear momentum before the collision and after the collision are same, we can say that the collision is a completely elastic collision. And both the things, right, not only the linear momentum but also kinetic energy before the collision and the kinetic energy after the collision are same. So if the linear momentum and the kinetic energy before the collision and the after the collision are same, the collision is said to be a completely elastic collision, right? So in that, the change in the linear momentum is 0 and the change in the kinetic energy is 0. So suppose a one collision is given to you for an example, right? A object having a mass 2 kg moving with the velocity of a 3 meter per second, colliding another stationary object of a mass 10 kg. After collision, the velocity of both the object is given to you. So you can easily find the collision is a elastic collision or a inelastic collision, right? So calculate the linear momentum before the collision, calculate the kinetic energy before the collision, calculate the linear momentum after the collision and kinetic energy after the collision. And if the linear momentum and the kinetic energy are same, we can say that the collision is a elastic collision, right? Now, what do you mean by the inelastic collision? So, in the inelastic collision, during the collision, if the linear momentum remains same, but the kinetic energy are different, such collision is called the inelastic collision. So, in the practical base, we can think about that. If the linear momentum of the object or system of object remains same, but the kinetic energy is used or lost some type of the kinetic energy due to the friction, right? The kinetic energy is reduced, or in the some collision the kinetic energy is converted into the heat energy. So some amount of the kinetic energy is lost during the collision, and such a type of the collision is known as the inelastic collision. In inelastic collision, the linear momentum before the collision and the linear momentum after the collision are same, but the kinetic energy, some of the kinetic energy is converted into the heat energy, some of the kinetic energy is used in the work done during the friction of the two colliding bodies, right? So some of the kinetic energy lost. So in the inelastic collision, the linear momentum are conserved, but the kinetic energy is not conserved, right? So here not conserved, that means the conservation of the energy, law of conservation of the energy is satisfied, but the some amount of the kinetic energy is converted into the other form of the energy, right? So in this type of the collision is known as the inelastic collision, and in this type of the collision linear momentum are conserved, but the kinetic energy before the collision and after the collision are not same. Understand? So now, dear student, we will discuss how we can find the final velocity of the object after the collision in a elastic collision and in a inelastic collision. How we can calculate the kinetic energy before the collision, after the collision, in the inelastic and elastic collision. So let us see that inelastic collision in a one dimension. So one dimensional motion, then the object is moving in a only one dimension, right? Only straight line. So consider the two objects having a mass m1 and m2 colliding completely inelastic. Completely inelastic. That means the kinetic linear momentum before the collision and after collision are same, but the kinetic energy is not same. So here, if we consider the object m1 having the velocity v1I and object m2 having the velocity v2I, if the object m2 we consider stationary, we take the velocity v2I is equal to 0. So here this, if these two objects is colliding with each other, after collision, the object m1 is moving with the final velocity v1f in the same direction, and after collision, m2 is moving with the final velocity vf. So both the object is moving with the same velocity, right? How we can find the final velocity of this object? So here the collision is completely inelastic. So we need to find the linear momentum before the collision and after the collision, kinetic energy before the collision and after the collision, right? So before collision, linear momentum is pi is equal to m1 into v1I plus m2 into v2I, but here second object is stationary, so v2I we take a 0. So before the collision, linear momentum pi is equal to m1 into v1I, right? Now final momentum. So linear momentum after the collision Pf is equal to m1 into Vf and m2 into Vf. So here consider that both the object is moving with the same final velocity. So we get Pf is equal to m1 plus m2 into Vf, right? Now kinetic energy before the collision 1 half m1 v1 I square, and kinetic energy after the collision 1 half m1 vf square plus 1 half m2 vf square. So we get kinetic energy after the collision is 1 half m1 plus m2 into vf square. Now here the collision is completely inelastic. That means the law of, according to the law of conservation of linear momentum before the collision and after the collision are same, but the kinetic energy are not same, right? So here the collision is completely inelastic. We consider the initial momentum is equal to final momentum. So initial momentum m1 into v1I is equal to m1 plus m2 into vr. So from that we can easily calculate the final velocity of the object. Vf is equal to m1 v1I divided by m1 plus m2, right? If the both the object is moving with the same velocity, right? Now the collision is completely inelastic. That means the during the collision kinetic energy are not same. So change in the kinetic energy, how we can find the change in the kinetic energy? Delta k is equal to ki initial kinetic energy minus kf, that is the final kinetic energy. So initial kinetic energy, that means kinetic energy before the collision 1 half m1 v1I square. So 1 half m1 v1I minus 1 half final kinetic energy m1 plus m2 into vf square. Now put the Vf final velocity Vf is equal to 1 m1 v1I divided by m1 plus m2 in this equation. We get the 1 half m1 v1I square minus 1 half m1 plus m2 Vf square. Instead of this Vf square, we place m1 v1I. So m1 square v1I square divided by m1 plus m2 whole square. 1 m1 plus m2 is cut out. We get a 1 m1 plus m2. And take a 1 half m1 v1I square common. So 1 half m1 v1I square common. We get here 1 minus. Here 1 m1 is taking common, m1 divided by m1 plus m2, right? So simplify this equation, we get 1 half m1 v1I square into m1 plus m2 minus m1 divided by m1 plus m2. So the change in the kinetic energy delta K is equal to 1 half m1 v1 I square m2 divided by m1 plus m2, or we can write like this also, delta K is equal to 1 half m1 m2 divided by m1 plus m2 into v1 I square. So this way we can find the change in the kinetic energy, right, and final velocity of the object, right? Understand, dear student? So now, dear student, we will see a elastic collision in a one dimensional. After the inelastic collision in a one dimensional, we will see a elastic collision in a one dimensional. So what is the inelastic collision? In the inelastic collision, the law of conservation of the linear momentum satisfied. So initial momentum is equal to final momentum, but the kinetic energy are not same. Initial kinetic energy and final kinetic energy are not same, but instead of that, in elastic collision in a one dimension, so during the elastic collision, the total linear momentum and the kinetic energy remains same before the collision and the after the collision. So in a collision, before the collision and after the collision, if the total momentum and the kinetic energy remains same, the collision is said to be a elastic collision. So for that, consider a object m1 moving with the velocity v1I and object m2 stationary. So we can take the velocity v2I is equal to 0. Both the object m1 and m2 are colliding at a some instant, and after the collision, the velocity of the object 1 m1 is a v1f and velocity of the object 2 is a v2f. So in this type of the elastic collision, law of conservation of the linear momentum is same, right? Linear momentum before the collision and the linear momentum after the collision are same, as well as the kinetic energy before the collision and the kinetic energy after the collision are same. So we need to find the before the collision linear momentum pi is equal to m1 into v1I plus m2 into v2I, but v2I is equal to 0 because the second object is stationary, right? Kinetic energy before the collision Ki is equal to 1 half m1 v1 I square plus 1 half m2 v2 I square, but here v2 I is equal to 0, right? After the collision, the velocity of m1 is a v1f and velocity of m2 is a v2f. So linear momentum after the collision pf is equal to m1 v1f plus m2 v2f. Similarly, kinetic energy after the collision kf is equal to 1 half m1 v1f square plus 1 half m2 v2f square. Now for the elastic collision, the linear momentum before the collision and the linear momentum after the collision are same. So from this above equation, m1 v1I, that is the linear momentum before the collision, is equal to m1 v1f plus m2 v2f, right? That is the linear momentum after collision, and kinetic energy is also same. So in the elastic collision, kinetic energy before the collision Ki is equal to kinetic energy after the collision. So if you put the value 1 half m1 v1I square is equal to 1 half m1 v1f square plus 1 half m2 v2f square. So we get 1 half cut out in all the term. So we get a m1 v1I square is equal to m1 v1f square plus m2 v2f square, equation number 3. Now substituting the equation 1 and 3, right, by a substituting method. So in the equation number 1, right, multiply by a v2f. So equation 1 is multiplied by a v2f. We get a m1 v1I v2f is equal to m1 v1f v2f plus m2 v2f square, right? And equation number 1 m1 v1I square is equal to m1 v1f square plus m2 v2f square. So substituting these two, we get, neglect this term, cut out this term, we get m1 v1I common in these two terms, v2f minus v1f is equal to m1 v1f common in this term, v2f minus v1f. right? So here we get V1I into V2F minus V1I. Here V1I common is equal to V1F, V2F minus V1F. So open this bracket, we get V1I, V2F minus V1I whole square is equal to V1F, V2F minus V1F whole square. So take this V1F whole square on the opposite side, right? So we get V1I, V2F minus V1F, V2F is equal to V1I, we take this side, V1I square minus V1F square. So here in this term we take the V2F common. So V2F bracket V1I minus V1F is equal to V1I square minus V1F square. Here we apply a formula A square minus B square. So we get V2F into V1I minus V1F is A square minus B square, that is A minus B, V1I minus V1F, V1I plus V1F. So V1I minus V1F cancel out. So we get V2F, the velocity of the final velocity of the second object, V2F is equal to V1I plus V1F, right? Now from the equation number 1 we get the V1F, right? Now from the equation number 1, what is the equation 1? M1 V1I is equal to M1 V1F plus M2 V2F. So instead of this V2F, put the formula V1I plus V1F and find the V1F. So M1 V1I is equal to M1 V1F plus M2 into V1I plus V1F, right? Now, on this, open this bracket, M1 V1I is equal to M1 V1F plus M2 V1I is equal to M2 V1F. So take the M1 V1F, M1 V1F and M2 V2F. In this term, take the V1F common and take this term in the other side. We get the M1 minus M2 into V1I is equal to M1 plus M2 into V1F, right? So from that, the final velocity of the first object V1F is equal to M1 minus M2 upon M1 plus M2 into V1I, where V1I is the velocity of the first object, initial velocity of the first object, right? Understand, dear student, how we can find the final velocity? Now from this, V1F is equal to V2F minus V1I, right? So M1 V1I is equal to M1 V1F plus M2 V2F, that is the first equation. And in this equation, put V1F is equal to V2F minus V1I, we get the velocity of the second object. The final velocity of the second object V2F is equal to 2 M1 V1I divided by M1 plus M2. Now we get here the final velocity of the first object and the final velocity of the second object after the collision. Now consider the special case when both the object having the same mass. If m1 is equal to m2 is equal to m, v1f is equal to m minus m divided by m plus m, we get the 0, right? So if both the object having the same mass, the final velocity of the first object becomes 0 and final velocity of the second object is equal to final velocity of the first object v1I, right? Now case number 2, when the two objects are colliding with each other, the first object is very smaller than compared to the second object, right? So here the object having a mass m1 having a very less mass compared to the object having a mass m2, and if they are colliding with each other, so neglecting the mass of object 1 compared to the object 1, we get the final velocity of the first object, it is equal to minus m2 v1I divided by m2 is equal to minus v1I. It is exactly the same as the velocity of the first object, but it is in the opposite direction. But in the second object does not move in the direction of the motion, right? So the final velocity of the second object be a 0. So now dear student, similarly we can understand the collision in the two dimensional. In the first previous case we take the collision in a one dimension, only the objects are moving in the same direction, right? But we can also understand the collision in the two dimension, in that the linear momentum we take the vector quantity, right? but kinetic energy, kinetic energy is a scalar quantity, so the equation of the kinetic energy is same as the previous case, right? But here in this case we take the equation of the linear momentum in the vector form. So for that, consider the two objects having a mass m1 and m2 moving with the velocity v1I and v2I, right? So here we use the momentum of the first object is in the vector form. So p1I momentum is equal to m1 into v1I vector. The magnitude of the first p1I is equal to m1 into v1I. So second object is a stationary, so v2I we take as 0, right? Suppose during the collision, the total linear momentum and the kinetic energy is conserved. So how we can write the equation? So before the collision, Pi initial momentum is equal to P1F vector plus P2F vector, and after the collision, the initial momentum P final momentum Pf is equal to P1F plus P2F. But in this case, we need to represent the momentum in the form of its component, right? So here the initial momentum Pi, so initial momentum Pi is in the direction of the positive x direction. Let us consider, right? So x component, it has only x component, so m1 v1 I, but here the final momentum m1 p1f is equal to m1 v1f. It is makes the angle theta 1 with the x axis. So we take the two component of the final momentum, right? A horizontal component and the vertical component. So here the horizontal component we take x component, so m1 v1f cos theta 1 plus m2 v2f cos theta 2. Similarly y component, so as the object 1 is moving in the positive x direction, y component of the initial momentum is a 0, and x component, y component of the final momentum we can find with the help of the sin theta. So 1 half m1 v1 f sin theta 1 minus m2 v2 f sin theta 2, right? Kinetic energy, the equation of the kinetic energy be written as the same as in the previous case. Before the collision, ki is equal to 1 half m1 v1 I square, and after the collision kf is equal to 1 half m1 v1 f square plus 1 half m2 v2 f square. Now for the elastic collision, the kinetic energy is same, right? And for the inelastic collision, the kinetic energy is a different, but linear momentum in all the case be a same, right? As the for the elastic collision as well as for the inelastic collision, right? Understand, dear student? So remember one thing, for the elastic collision, the linear momentum and the kinetic energy both are equal before the collision and the after the collision. But for the inelastic collision, linear momentum before the collision and is same as the linear momentum after the collision. But the kinetic energy is somehow different. And the difference in the kinetic energy is lost in the form of the some other type of the energy, right? So understand what do you mean by the elastic collision, what do you mean by the inelastic collision. Thank you very much for watching my video.